width of 3.5. And there's some sections where you don't have numbers. Do we put zeros down?
Yes, absolutely.
I didn't know if you wanted to.
No, if you start creating a relative, if you start creating a grouped set of data, and you're using 0 to 2.5, and then 2.6 to 5.0, and 5.1 to 7.5, if any of those have a frequency of 0, they still have to be there. Once you create a pattern, the pattern has to always be repeating. So even though there's nothing in there, just work with it as a 0.
So then in the cumulative, would it still be the next number in front of it still?
Well, no, then the number just repeats.
Okay, so like,
So if the cumulative frequency for the class before it was 10, the cumulative frequency of the class was 0 will be again 10.
okay,
Because you add 10 to 0 and you get,
that's what I was questioning.
yes. It's one of those where it's weird, so you don't necessarily know if it's right, but it's math, so you're going to continue to follow the same pattern. And when you add 0, just remember you know how to do it. All right. Any other questions about group frequency and whatnot? Okay.
Oh,
So-
yeah.
Yes, that's okay.
If your thing starts with 0, what would the class boundary?
Okay, good question. So let's suppose that we had this, just these 3 classes in our frequency range. That's all we care about, right? So here's our class, and suppose our frequency, who cares what the frequency is, right? 5, 2, 8, whatever. And now you want to do class boundaries next. How do we do it again?
Minus whatever the rate, or whatever your class, no, not class, what's the width, right?
Don't you just take 2.5 and 2.6 and then you put 2 after you have
Yes, so figure out the average between each successive upper boundary and lower boundary, right? So we say, oh, 2.5 plus 2.6 is 5.1, divided by 2, 2.55, right? So the upper range of the class boundary is 2.55, and the lower range of the other class boundary is 2.55. Rinse and repeat, right? So do it for the next one, between 5.0 and 5.1. You have created a pattern now, right? What am I doing to get from 2.55 to 5.05? What am I doing to get from here to there? You're adding 2.5, right? So what do I do to this to get to the next number down here? Add 2.5. So even though I don't have an upper range to calculate the average with here, because you've created a pattern, you can do it, all right? And so going the opposite direction, right? Uh-oh. Oh, did I move it somewhere? Okay. There we go. That's a little bit better. What am I doing to go from range to range? The same thing, so where am I going to start down there? So the idea here is that you're setting up a pattern, and once you set up a pattern, rinse and repeat the pattern, okay? And I should have really called this 0.1, sorry, it's a little inconsistent. But that's the idea behind creating the first and the last upper and lower boundaries of your class boundaries is. See the pattern, rinse and repeat the pattern. And don't freak out. If the pattern gives you a negative number, it is perfectly okay to have a class boundary that is a negative number. Even though all of your numbers over here might be positive, if your class boundary is negative, that's fine. Nothing wrong with negative numbers. You like them, okay?
If they want you to start with class of zero, is it just zero?
No. It's got to follow a pattern. So if I made this one really zero, if I had one that was zero, right? So if I have, erase some of this. So I have 0, 1, and I have 1.5, 2, and I'm adding 1.5, so 2.5, adding 1.5. I have to be careful, make sure I do it correctly. So I'm going to 1, 2.5, this is weird, but don't worry about it. I can't add. Don't ask me why you would have ranges like this, but imagine if you did. Again, what would be your class boundaries here? So what is the average of 1 and 1.5? 0.25. What's the average of 2.5 and 3? And so what am I doing? Same, adding 1.5. So I add 1.5 to this. I subtract 1.5 from this. So it can be negative up here in that initial class boundary. That's what I'm trying to get to, okay? So once you see the pattern, just because the pattern winds up being negative, do not change it to 0, because that's not following the pattern, and therefore it would be wrong, okay? That is a standard sort of misnomer, too, is that students are like, well, why can I be below 0? You can let it, all right? All right. So we feel relatively comfortable with negative class boundaries. You will have that on the homework, so if you don't, look at it. All right? So when you show that table with all of that information in it, midpoints, class boundaries, frequencies, relative frequencies, cumulative frequencies, relative cumulative frequencies, having those datas in your reports when you're talking about statistics is a good idea. But just like almost everywhere, when you have a table full of information, folks, most people look at the table and their eyes roll up into their head and they go, oh my God, that looks like a whole bunch of numbers. I don't want to deal with them, all right? So in order to alleviate the stress that people have from looking at a table of numbers, what do you do instead, or in addition? You make pictures, right? And you put colors in it. Because when you put colors in pictures inside of a deep mathematical report, all of a sudden it's not quite as scary as it was before. Even though it is still just as scary as it was before, it now looks nicer.
It's pretty.
It's pretty. And pretty it just makes us feel more comfortable. It's just part of life, right? So you want to graphically display data as much as possible. So one of the classic things that you can use to display data, pie charts. Raspberry, folks, that's my favorite pie. And not raspberry rhubarb either. That ruins the raspberry. Straight raspberry. That's mine. That. Actually, had a student one year who brought in a raspberry pie. I gave him an A.
Was it National Pi Day?
It was on Pi Day too.
That was symbol of pi instead of pi.
Oh, he didn't do that. Oh, that would have been over the top, but it would have been okay. All right. So, anyways, pie charts, folks. When you are working with pie charts, use the relative frequency to determine out what percentage of each piece is the pie. Okay. That's when you show a pie chart. You should have the column relative frequency in your table. Okay. And this is sort of what drives how you guys should be putting the information in your table. Okay, any chart or picture that you use that requires that data in it to explain the chart, that's when the column has to be there. So if the only thing you put in your table or in your report or whatever it is that you're writing is a pie chart of your data, in theory, a lot of the information in the frequency distribution you don't need. So all of that midpoints and class boundary stuff, not necessary, because you're not actually using it in any other part of the actual paper. So if you're not using a piece of information, you don't necessarily have to show it. You still can, it's just you don't have to, okay? So just keep in mind as I go through this, each specific type of chart is going to sort of force you to show or use certain pieces of information. And if you use it, it had better be in your table, your frequency distribution table that you showed initially, okay? So just be careful with that one, all right? And again, it's not 100% mandatory, but it's one of those things that if you do it, your report looks that much cleaner. So that when people look at a graph, they can also say, oh, here's the data where that graph came from, bam, right? So when you say that a certain piece of the pie is 22%, they can go back and look and say, oh yeah, here in that relative frequency table where they had 2/9 and said that equals 22%, they can see the information in a table as well as in a picture. And those things are reinforcing to the paper being legitimate, okay? So it's one of those where I'm never sure how many of you are actually going to get a chance at some point in your career later on to actually write a statistical report. But I would hope that all of you would at least try to once. And these are the sorts of things you have to think about when you go about doing it, all right? So that's pie charts. So, where did that happen? Did I go backwards or something?
Yeah, we had a little pull-up menu there.
Did I? Okay, that was weird. All right, so. All right. So bar charts or bar graphs. Note that these bar charts or bar graphs I'm talking about, the bars are separated, so there's a space between the bars, as opposed to the bars being very close together or actually touching, all right? I would like to think that you guys would know how to do a bar chart without me really explaining it. But a bar chart is where you draw a bar for each frequency, and you label the frequency, you label the chart below. Let me just do one really fast to be safe, okay? So let's suppose, I should just do it just to be safe, okay? So let's suppose we had 0 to 10, and I should be careful. 0 to 9, 10 to 19, 20 to 29, and say 30 to 39. And these all have some frequencies, 6, 2, 7, 5, whatever. It's just information. When you're creating a generic bar chart for this particular data, in general, folks, it is usually more pleasing to the human eye to have bar charts that are vertical as opposed to horizontal, okay? You don't have to follow that if you don't want to. You can use horizontal bars if it makes you feel better, right? Bars that are going right and left, but I will generally do them going up and down instead of right and left, okay? So frequency, let's see, so 3, 6, 9, and your data. Now, when your data is in a grouped frequency table, you create a bar for each one, and you label your entire bar with your class, okay? So literally put in, this is the 0 to 9 class, and it goes up to 6. And then you have a separator, and this is 10 to 19, right? So the bars are separated, and your classes are completely displayed inside of your data, okay? And again, this is 20 to 29, and whatever, 30 to 30. Okay, so again, I was just being safe by drawing that. I apologize a little bit.
What is that?
It's just a bar chart, right?
Sure.
Okay, so just a regular old bar chart, right? Now, if there is additional information inside of this bar chart, so imagine, if you will, that 0 to 9 means something. Like it means that, you want to say that the group people in this group from 0 through 9 are above average, because a low score means you did well, all right? How would you indicate in this bar chart that this is above average, these two are, say, generically average, and these scores are below average? How would you indicate it on the graph? Except in this kind of graph, they call it a legend. A legend, right? So a legend is a separated piece of a bar chart area where you put in additional information if necessary, right? So if you want to say that this bar represents the number of above average people, you would somehow want to connect those two. Now, how can we connect something that's up here with something down here? Colors are generally what we use. Why do we not use colors anymore, though? Yeah, because unfortunately, like 15 to 18% of all men are at least partially colorblind. Yeah, it's more men, folks. Women, for whatever reason, you guys are much better with colors. Only 5 to 8% of women are colorblind, but men, 3 times the rate. It's us. We're the problem. Sorry, folks. Which shouldn't be all that surprising. So the way you would do it nowadays is you use patterns. So you'd make the bar have vertical slashes in it, and so up here you'd say, oh, vertical slashes, these are above average. Or whatever it may represent, right? Whether it represents some class of, whatever data you're gathering, whatever, right? And then again, you just do, if both of those imply average, it's okay to have both of these have the same pattern. It's not wrong. It's a little weird, but it's not wrong. That's average, and then perhaps sad faces, because those are the below average people. And you can be a little creative because it's a math class, and so you got to try, right? So here are your frowny faces. Those are your below average people that you sample. Whatever, okay? Just whatever you want to do, you can do it. Just use patterns, not colors nowadays. All right, so bar charts. that's okay, right? I mean, this makes sense, right? You guys are making me a little nervous because you're all dead.
It's pretty simple, Marshall.
Okay? Okay. All right, so a Pareto bar chart this is an organized bar chart where the bars start at the highest level and progress to the right to the lowest level. So it's a slightly special type of bar chart where you have forced a certain pattern onto the actual bars in your graph. So a Pareto bar chart looks something like this, where the tallest bar is always going to be first, the second tallest bar is second, the third, the fourth, the fifth. However many classes you have or however many bars you have, you just make sure they're in a descending order, all right? Now, why would I have a problem in this bar chart I drew here just a second ago with making this a Pareto bar chart? Yeah, my data, which is 0 to 9, 10 to 19, 20 to 29, 30 to 39, would not be in order if I created a bar chart that way. When your data needs to be sequential, leave it sequential, don't make it a Pareto chart. But if your data that you have gathered is information that's generic, like suppose these bars, instead of representing the 0 through 9, they represent eye color. And this is really blue, this is green, this is hazel, and this is brown. When it's like, when the order that you put these in doesn't matter because the stuff isn't necessarily related, that is when you use a Pareto bar chart, all right? For data that is nominal. Where you're filling out some sort of a category, and the categories are not related in any way, shape, or form, then the order doesn't matter, right? Because it doesn't matter which one comes first, which one comes second in the actual chart itself. So in your table, you may have had this be the last class in your table, but when you show it in the picture, it can be the first class in your picture because it doesn't matter what order they show up in, right? Because eye color, does it matter whether you go blue, green, brown, red? No. So you may want to choose to do that. Again, Pareto bar charts, you want to use these anytime you are working with nominal data because it just makes your graph look more real, okay? It's sort of weird, and again, this is the sort of thing that I actually did analysis on when I was going on my graduate degree in applied mathematics in economics. We wanted to see, when people look at a graph, what sorts of graphs do they like and what sorts of graphs do they not like? And that's all we asked them. We showed them a graph and said, which of these graphs do you like and which of these graphs do you not like? And all we had were different types of bar charts. And it was weird. It actually worked out that when you had the bar charts such that the bars started big and went down small, everybody liked, the percentage of people that liked it was always higher than the percentage of people who didn't on the other ones. Don't ask me why. I don't know. I don't do psychology. I was just doing the statistical analysis of it. A bunch of other people were writing the paper about why. I have no idea why. I never actually got the paper, so I don't know. But, I mean, we did it, and I was just looking at the data going, wow, who would have thought? But that's why they actually have named it something special, okay? Because they noticed it, so they used it, all right? Again, it's sort of weird, but it is what it is. All right. Now, so there are other types of bar charts that you can have. When you have more data as a subset of your regular sets of data, you may start creating side-by-side bar charts or stacked bar charts. Again, I'm sure you've seen things like this before, but I just pointed out so that when you get to this stage of working on a report, you don't forget about it. The idea here is that suppose you were getting the color of people's eyes in a specific classroom, okay? And so you're figuring out, okay, there's 8 people in this classroom who have brown eyes. But note that in this classroom we also have men and we have women. Might it be a good idea while we're gathering our data to gather which of those brown-eyed people are men and which of those brown-eyed people are women? Yes, you will almost assuredly have that information. And so the question is, when you say, oh, here are my brown-eyed people from this study, should you put the male and female side by side, or should you stack them on top of each other? Which do you think you should do? Why? Why do you think it should be side by side? It just looks a little bit better, so maybe you would say, okay, here are men, and let's suppose here are the women, right? So you just put them side by side, right? And you have to make sure that you indicate that they're side by side, okay? Whatever, right? And then you would say, oh, okay, here come the green-eyed people, and here are the men, and here are the women. And again, maybe you're doing some statistical analysis about eye color and sex in pick your favorite topic, okay? Now, why would I want them side by side? Why would you change this to stacking? Potentially. Yeah, if you cared more about what the total number of people are that have brown eyes, you should probably stack this. If your paper is talking more about a comparison of the color of eyes and the relationship between the gender of the student or person, whatever, then you want to have them separated. Again, it's one of those where it depends on what the focus of your particular paper is. If you're doing a comparison of gender and eye color, separate them. If you're really just comparing the total numbers, you should stack them. But again, you still want to show that you gathered that information to people, so that's why you may separate them instead of just having one bar that says, here were the number of people with brown eyes. Okay? So you want to give as much information as you can inside the graph, because that will almost always stick with the crowd who's looking or hearing about what you're doing. And if you can get more of it to stick, you've done a better job. That's just the way it works. All right? So again, it's just one of those where focus on what it is that you care about, right? Use the style that matches the discussion in your report. And again, these are, this can apply to lots of different categories, right? So you're almost always going to have the data, right? A lot of times if I would have been teaching this class 25 years ago, I don't think my professor even talked about the difference between stacking and side-by-side bars. Because very rarely do we actually ever have all that data. So if we were looking at the color of eyes of a student, they just got the color of eyes of the student and counted it, and that was it. They didn't care whether they were male or female, or gender neutral, or whatever they were using, right? So these sorts of things, now that we're in an era where data is gathered more, are more likely to be used. Okay, so you guys have to actually worry about it a little bit. Alright? Alright, so again, it's just one of those where think about it, use it as needed. Alright, so next type of way you can display graphical information is using a histogram. Now, the cool thing about a histogram is that it's actually another bar chart. But it's called a together bar chart. So the bars are actually touching. Whereas in all of our bar charts before, they were separated, right? Each class had a separation between class to class to class. Here is where you have the bars touching. This tends to be the more classical style of displaying bar graph data, is using a histogram. If you've seen them out there, generally this is the way they will be done, more often than not. If the data that they're gathering is numeric. Again, it is tied to the numbers being numeric. So, how it works. You use either the midpoints of each class or, not with an E, just OR. That's a B, even though it looks like a class boundaries. It's really up to you as to which one you want to use. But the idea is just that you set up the bars such that each bar is defined between either the class boundaries or directly above the midpoint, whichever way you want to do it. Okay? So, since I have examples in the book, I should just use them. So if you go back into 2.2, say the homework section, let's see. What numbers did I assign in 2.2?
2.1, 2.2, sorry.
Yeah, 2.2.
2, 4, 8, 10, 12, 22, 24.
All right, so let's suppose that we were going to do question number 9. So in section 2.2, I want you to create, or we are going to create here in class, a histogram for this specific data. All right? Now, do our classes, right? So it's 0.05 to 0.07, 0.08 to 0.10, 0.11 to 0.13, 0.14 to 0.16, and one more 0.17 to 0.19. Now, these things all have a frequency. 12, 15, 14, 15, 14, whatever. Now, first off, what are their midpoints? .06. What's the next one? 0.09. And now what's the pattern? What am I doing every time? Adding 0.03, rinse and repeat the pattern, right? So don't calculate the average every time. Once you see the pattern, use it because it's almost always easier, right? If you're going up by 0.3, just keep adding 0.3, 0.12, 0.15, 0.18, okay? These are the sorts of things that if you actually really had to do this by hand, you had better be taking advantage of, all right? So what are my class boundaries for these? .075, .075. .105, .105. Notice, what's the pattern, folks? What? What are we doing to get from .075 to .105? Adding .03. What were we doing in the other one? The same thing. It's always going to work like that. Math is full of patterns repeating itself over and over and over again. So honestly, once you've done the midpoint, the class boundary, you should really only do an average once. Because then you can just use the exact same pattern from the midpoint to calculate all of your other numbers. Okay? So, 0.135, 0.135, 0.165, 0.165, 0.195, and up here subtract 0.03, 0.045. Again, that's the way these midpoints and class boundaries work. It's a pattern. Use the pattern to your advantage, right? So now, again, which one do you use? The midpoint one or the class boundary one? That one I don't know, folks. Use whichever one you like better. Again, though, use them the way they're meant to be used, okay? So if I had to graph this particular set of data, if I was using the midpoint, 0.06, 0.09, 0.12, 0.15, 0.18. The midpoint, by definition, is the middle point. So when you draw your bar so that this number is in the middle of your bar. Because that's what midpoint means, right? So I need 12 of this first one, so here is 12, right? 12. The next one at 0.09, I have 15. Here's 15. And note, the bars are exactly touching, right? You just basically continue off to the next one. 0.12.
Basically, you're going off the frequency.
Yes, always you're graphing the frequency, yes.
I got that.
Right, so that's why you need the midpoint. It's just where do you draw the bar, okay? For each frequency, that's it, right? That's one way to do it. The other way to do it is instead of using the midpoint, what can I use? The class boundaries. Where would I write the class boundaries? At each edge of the graph, right? I would say, oh, this over here, this line is 0.045. This line is 0.075. This line is 0.105, 0.135. 0.165, 0.195. And you can do either one. You can either use the midpoints or you can use the boundaries. Usually they don't use both because then it gets a little too cluttered along the bottom of the graph. But the whole point of a bar graph, Abby, is really to just show the frequency. I mean, that's the whole point.
I just don't get why you do the midpoint anyways if you're putting the bar up to that point of frequency.
Well, but you need to know what this represents, right? There's 12 numbers that are basically 0.06. There are 15 numbers that are basically 0.09. right? So that's the idea, is that they're trying to tell you how many of this number are there. And so if you put in the class boundaries, then you're saying, oh, I've got 12 numbers that are between 0.045 and 0.075. I've got 15 numbers between those. Again, that's the idea. And again, in theory, whichever one you're sort of more focused on, whether it's sort of a generic analysis and so using the midpoints is okay, that's when you might use it. If you're going to talk a little bit more about things being between values, maybe you want to make sure that your histogram shows that there are boundaries to these ranges, et cetera, right? Again, it a little depends on what you're trying to do as to how you're going to display the data. But either one, perfectly okay. And it's just a method to show the frequency, which is in theory what everybody cares about, in theory. All right? So, again, it's one of those where if you haven't had to work with these sorts of things before, sometimes it's a little like, why are we spending so much time on this? But when it comes down to actually writing a paper and having to then show people pictures of what you're doing, this starts to become a bigger deal. All right, so another method that you may use. Oops, I'm blue. You may use a way to display the frequencies by using a frequency polygon instead. So normally if you're done looking at bar charts, which we are now done, instead of using a bar chart, you may decide to use a line chart or a line graph. So a polygon frequency diagram is going to be a line chart, okay? In general, when you're working with frequency polygons, you tend to use the midpoint because you don't want to have the boundaries, because then you would have to sort of have this step ladder function that doesn't make sense. So we tend to use the midpoints of each class. A lot of the points of our line chart or of our line graph. And what we do, because it's called a polygon, is you add an extra class at the end and the beginning. To create the, and I will put it in quotes, polygon effect, or is it the polygon effect?
Stick with the E.
You're right, yeah. I like the A better. I think it's the polygon effect. Right. I agree. Effect is more active. Alright, so you'll see why I mean this in a little bit, right? So again, the idea is that you're trying to draw a line chart of your frequencies, okay? So let's use the same example we were working with just a little bit ago, this number 9. Except instead of creating a histogram, let's create a frequency bar chart, okay? Let's use the number 9 data above. And what were my midpoints again? 6, 9, 12, 15, 18. Now, what did I say I had to do? Add an extra class at the beginning and the end. okay? So I want to start at 0.06, but I need one before it. So yeah, remember the pattern. You're going by 0.03s, so use the exact same pattern and create a fake boundary at the edge, okay? So we're going to start over here at 0.03, and then get into your actual data, 0.06, 0.09, 0.12, 0.15, 0.18, and yes, add an additional one at the end, okay? And our frequencies, perhaps a little exaggerated, but whatever. So how much data did we have at the 0.03 level? Nothing. So therefore, where do I put the dot? Yeah, right at the bottom of the line. Now 0.06, how much data did I have? That was the 12. 0.09 was that the 15? And then it did the 15, 14 thing. 15, 14, 15, 14, right? And then how many did we have at 0.21? Back to 0. And now you see where the polygon effect that I'm talking about, connect the dots. What sort of a picture do you draw? And now it looks like a polygon, okay? It looks like a regular shape where you just, the outside edge of it is the data that you're moving from point to point, and you always go down to 0 at the end to close the polygon, okay? That's all you're trying to do with a frequency line chart or a frequency polygon chart. It's a fancy way, folks, of saying line graph, okay? That's literally what it is. All right.
How come in like school when they're teaching you about these, they don't tell you about using midpoint? That's probably why I'm so like, why?
Well, because in school, it's a real pain in the ass to create these classes that are grouped, right? I mean, it's a lot of work, okay? And so most middle school and grade school teachers already have enough work dealing with middle schoolers and grade schoolers. And so I mean, you guys are all yawning already, so I know that I'm putting you to sleep by doing this. So imagine if you're doing this to a room full of middle schoolers. What would they be doing during this? They'd be poking each other and throwing shit around the room. I mean, come on, right?
Not anymore now, they have cell phones.
Yeah, true. They'd be,
Tablets.
yeah, they'd be playing a game of some sort or whatever. Or probably Snapchatting stuff that I don't want to know about, right? But I mean, again, this is
I think it'd make more sense if we did that in like younger age, we learn doing that.
yeah, this is not complicated. That's what I'm pointing out to you, right? But at the same time, it's the sort of thing where if you have to do this kind of stuff, don't forget about it, right? I mean, if you haven't seen this before and sort of these sorts of terminology thrown at you, when it comes at you, you're like, what the hell? Why? What is this, right? And so this is just me making sure you've had an introduction to everything at least once, even though it's a little on the dry and whoa, okay, another line graph. Oh God, right? I mean, bear with me, okay? All right, so we there's like two more. So is it just two? Yeah, just two more, and then we'll be done. And we can move on to something that's hopefully a little bit more exciting. All right, so. This is technically an ogive chart, by the way. That G sounds like a J. That That is just a line. Hey, quit being so smart. There we go. A line graph of the cumulative frequency. Why does cumulative frequency, why do you think you would want a line graph of cumulative frequency? That's absolutely right. If you draw a graph, if you draw a line graph of cumulative frequency, you're going to start somewhere low, and then what are you going to do? You're always going to go up. And folks, anytime you see a line graph like this, again, you can do statistical studies. Students who see this line graph, what do they think? It's good, right? Because the numbers are always increasing. This is awesome. Everybody loves this kind of a graph because the numbers are going up and to the right. We're making more profit, even though this has nothing to do with profit or money or anything. It still feels that way to a student who just looks at it, so they like it. Therefore, you will often see ogives written or drawn on certain, statistical reports. But that's the only difference between it. It's a line chart of cumulative frequency. And it's got a cool name, right? I mean, ogive. Yeah, that's just a cool name. Yes, it is a little silly at the same time. All right, now one last type of chart. Stem and leaf plot. Never sure if people have dealt with this one before, but stem and leaf plots. It's a way to display two-digit data in sort of a grouped method. So stem and leaf plots, basically the idea is if you have a bunch of data, so let's suppose this is my data. My data is, I won't make it too bad. So suppose it's 18, 19, 25, 28, 21, 19, 25, 30, 31, and 26. So suppose I had a class and these were their ACT scores or something like that, okay? And I wanted to show people this information without showing them a list of numbers separated in columns, okay? And I don't want to draw some silly bar chart or create some sort of grouped histogram data that just doesn't make a whole lot of sense. I just want to say, look, these are the numbers of ACT scores of my students in this class. So you have like 10 students, or however many that is, 2, 4, 6, 8, yeah, 10, all right? So a way that you can create the data is use the stem and the leaf approach, right? And the stem is the leading digit. So how many different leading digits do we have? And then what you put in the leaves are however many of those numbers you have with this leading digit to the right of it, right? So I had 118 and 219, so I'll go 8, 9, 9. That represents an 18 and 2 19s. And you do put the 9 down twice to say I've got it twice. And you do tend to try and put this in numerical order. You don't absolutely have to, but it's usually frowned on if you don't. So 20s, what would you do here? You would be like 1, 5, 5, 6, 8. And then 0, 1, okay? So it's just a clever way of showing two-digit data, and it's pretty clear just from looking at it what it means, right? You don't even have to understand what stem and leaf means to sort of get it. And it's a way of saying, hey, now I can sort of show you that, yeah, I had 3 people in the teens, I had 5 people in the 20s, and I had 2 people in the 30s. Okay? And I've seen those actually out in real reports in the last 10 years since I've been looking around at them. I mean, it's still used to some degree because a lot of our data happens to wind up being 2-digit data, and so it's a nice, easy way to show it relatively quickly.
I think that's the only one I have never seen before.
Never seen stem and leaf?
No.
Cool.
Learn something new.
So when on the button, it says a key, do we have to put a key?
Don't have to. It's one of those where it probably will help to explain what's going on, but honestly, that should be enough. All right. Not too bad. So that is the end of section 2.2. Thank goodness. Now, you are in the homework, folks, you are going to be asked to draw some graphs. I mean, similar to the really exciting graphs I was drawing here in class. How you create those graphs is entirely up to you, okay? If you want to mess around with a software package that will make creating these graphs on an Excel spreadsheet and then use it to draw your graph for you and print that out, I am perfectly happy with it, okay? If you want to do it all by hand, just like I did a little bit ago, that's cool too. You are more than welcome to. It's entirely up to you, okay? But I do want you to draw some pictures and try to have a little bit of fun while you draw bar charts and line graphs and whatnot as you are going through the data to sort of see where and how it might be useful to you sometime later on. Again, this is just me sort of making sure that we're all on the same page. All right, so. All right. That's a Z. So not only should you be able to create a graph, you should also be able to look at a graph and sort of understand how to describe the graph as needed. So if you get a frequency graph that looks something like this, let's suppose it's a histogram, and the data looks something like that, where it's all kind of at the same height. What would you say about the data that you have gathered? Uniform data, because the frequency of each class is very close. It doesn't have to be exactly equal to be uniform. It's obviously nice if it's all exactly equal, but as long as it's close, you can say that it's uniform. You may have other data that looks like this. Let's suppose I draw this one as a regular separated bar chart. What would you say this data looks like? Kind of a bell curve, and so what do we say a bell curve has? Yeah, it has symmetry. This is symmetric data where it's the same on one side as it is on the other, right? So if you folded this graph in the middle, everything on the right-hand side of the graph would fold over to the left-hand side of the graph and be on top of each other, hence it's symmetric. It's also a funny example because it also looks like somebody's flipping me off. That's the type of humor you gotta look for when you're spending an entire day talking about graphs, folks. It's a little on the dry side, okay? So, the graph can be folded and fit on top of each other. However you want to define symmetry, whatever the classier way of doing it is. I can't give you the Webster's dictionary definition right now, but that's what symmetry means. And note that it doesn't have to look necessarily like that. It could also look like that, right, where it's smaller in the middle and wider on the outsides. And note, folks, that technically, uniform data is also symmetric. It's just a little bit more powerful to call it uniform than it is to call it symmetric. Uniform is basically telling you it's basically always at the same height, whereas symmetric just means that it's reflecting itself at some point in time. All right? All right, so those are sort of the two classic. And then one of the other terms that you will hear is skewed data. Skewed is actually a technical term in statistics, it really is. And the idea behind skewed data is that when you look at the graph of the frequency, again folks, all of this is based on frequency. So the idea is that all of the frequency is bundled on one side of the graph, okay? And now, this is where it gets a little bit on the weird side, folks. This is skewed data. You could have data that's either skewed left or skewed right. Which one would you think that this is called? Why? If you're looking at the book, you can see that this is actually called skewed right. Why is that? Not technically, no. The reason why we call it skewed right, folks, is that the problem with this particular number is that what we really care about is the average of the data, okay? And it's the average of the data compared to where the middle of the data is. So it's comparing mean to median, okay? Which I know we haven't talked about, and that's in chapter 3, but I'd like to think you understand this. The idea here is that the average of this information is going to be skewed to the right. It should be where most of the data is. So here would be what we would consider the middle, somewhere right around in here. But the actual average will be pushed off to the right a little bit because of these extra outliers sitting out on the edge of the data, okay? So it's skewed to the right because all of the data is not sort of bunched right with where most of it is. So it's these small things that determine your skewing, okay? And that can be a little bit deceptive because often we think the big stuff is what we care about, but it's really the small stuff that draws your skew in this particular case. So if you had a chart that looked something like this, where most of your frequency was a much higher number, but you still had some little small numbers out here off on the far left-hand side, this you would say is skewed left, because the average will be dragged a little bit closer to those small ones than it should really be. again, it's deceptive because we tend to think what's important is tall bars, but really here it's the small bars that are what are skewing us. Yeah, it's skewing us up. Yeah, so what is doing the skewing? Well, it's the small things, therefore that's the direction you're skewed. Alright? Alright, and then one last minor topic to talk about. Outliers. First off, what is an outlier? Outlier, folks. What do you think it is? That's the book definition. But what is an outlier?
The screwy stuff.
It's the screwy stuff. Yeah. I mean, it's the stuff that's way outside of most of the data that you gather, right? So if you have a bunch of numbers that are like 52, 58, 61, 60, 49, 51, 55, 61, and then all of a sudden you have a number 4,000, and then you go back to 54, 59, 58. Huh?
Random.
Yeah, it's like, where the heck did that come from, right? A number that is just nowhere within any sort of realm of reality for all of the other numbers that you gathered, okay? So basically, it's a data element that is weird. Weird, of course, does not have a mathematical terminology tied to it. But again, it's just a number that is outside of what we might consider the norm. And outliers are one of those things that statisticians actually still don't have a good grasp on necessarily. Some statisticians say that when you go to work with this data set, so if I was working with these 15 or 16 numbers, should I ignore the 4,000 or should I use it when I go to calculate data?
50-50 chance of being right here.
And even today, statisticians don't have a really good answer with that, because this number 4,000, it may be just a different group of people that you just weren't sampling. And so you sampled a whole bunch of sort of normal people, or what you consider to be normal, and their values, whatever it is you're measuring, were normal. And then all of a sudden you hit a group that is not a member, that is not sort of in the standard group. Does that mean that you should ignore them when you start talking about what's the average of this set of numbers, or what's the middle of this set of numbers? I mean, the problem with it is that if you calculate the average of these numbers with the 4,000 in there, what happens? Yeah, it's going to be a lot higher than what most of the numbers are, right? And that's going to make your, that could make your data look wrong. So should you just ignore it and do all of your calculations with the numbers that are all sort of grouped together? Yeah, I mean, that's a,
I just look at it as it's a piece of your data.
it's a piece of your data. You should really use it, all right? But what statisticians, and this is actually something that I've had to do in my own statistical studies, is that every now and then I'll have students in a class where everybody's getting between 60 and 100, and then I'll have one student who's regularly getting 20. And they don't drop, they don't quit, they just keep coming back, and they get 20s on, like, all the tests. Yeah, I can't advise anyone to drop my class. It's actually in my contract that says I won't do that. I can give them help, I can give them advice about life, but I can't say that part of my advice is that you should drop the class. I actually can't say that. Okay? But if you get, like a 21 and then a 24 and then a 22 on the first 3 tests in my class, yeah, you either need to start showing up or quit showing up entirely, whatever. But, so I actually calculate my statistics twice, once with the outlier and once without. And then I can say, I'll report, I actually create my own little mini report saying with outliers, without outliers. Because I do, I'm like, well, maybe this is a segment of the population that I really do need to have in the study, but it's just, I am not getting enough of them in my classes. I don't know. So, just realize that those things are out there, and again, should you use it, should you not use it, there, like I said, there's debate. Lately, people have been ignoring outliers. That's sort of been the mode of the last, say, 8 years, 9 years of data analysis, is that when you have outliers in the data, assume it's someone who is purposefully trying to destroy your data set, right? So they're, so they come in and say, on a scale of, 0 to 100, how do you feel? And they just write down 4,000, right? I mean, don't ask me why, they just did, right? So, anyways, that is section 2.3. So, for next week, folks, do the chapter 2 homework, 2.1 to 2.3. And we will go over some of it on Monday at the beginning of class, and then we will move forward into chapter 3 after that. Good?
Sounds like a plan.
And Monday I do plan on being out in Monroe, folks, just so that you know, so you can get a chance of one Monroe people dealing with me and people here dealing with me as the TV personality that I really am. Don't worry, I'll give you a weather report while we're out there. I'll be Bob Lindemeyer.
Yeah, don't get started right away.
Yeah, true.